Live from the Washington, D.C. area, it's the Inside Scoop. All the news that our viewers want to know. Now, here's the host.
Welcome to an Inside Scoop special. My name is Hina Kazmi. The topic of today's session is astronomy and big data. The fields of astronomy and astrophysics have been transformed in the age of big data analytics. The telescopes of the 21st century are designed to generate large volumes of multidimensional data sets. This capability has exponentially enhanced scientific research to study the cosmos, like formation of galaxies, stars, or searching for habitable planets, much like our very own planet Earth, and ultimately try to understand our place in this vast universe. In our show today, we will discuss how some of this cutting-edge research is taking place at George Mason University, right here in Fairfax, Virginia. The university is home to a number of space research centers and programs. Also, space exploration is one of the 6 core research areas under the Grand Challenge Initiative. As the university describes it, Grand Challenge Initiative is a comprehensive research framework to address humanity's ultimate grand challenge, which is to secure a peaceful, healthy, and prosperous future. And to talk to us about all of this is my guest, Dr. Ferah Munshi. She is an assistant professor in the Physics and Astronomy Department at George Mason's College of Science. Welcome, Dr. Munshi.
Thank you. Thank you for having me today.
I know this is the beginning of spring semester, so busy time for professors, so really appreciate you being here with us.
Of course, I'm happy to be here.
So let's start by first introducing you to the audience. Tell us what inspired you to go into astronomy, and what is your research area?
Sure. So I started college wanting to be a political science major. My dad always wanted me to do math and science, and I was a rebellious 18-year-old and said, no, I'm going to write and I'm going to study political science. And one day I misregistered for a course. I didn't understand the course catalog, and I thought, oh, this class has a smaller number. It must mean it's an easy class. And I thought an easy astronomy class sounds great. And it turns out that it was a class for majors, and that changed my trajectory. I ended up absolutely loving it, and I switched my major to astronomy. I called my dad to let him know that I did that, and he and my mom were actually in India. And I remember hearing silence and the phone kind of clattering around like they didn't know what to do. And so it was as much of a shock to me as it was to them, but you could say it was a very fortuitous accident that I ended up in astronomy.
And so your research area when you were doing your doctorate is what?
So when I was doing my doctorate, I was mainly interested in studying star formation in small galaxies, and in particular simulations of small galaxies. So these aren't real galaxies, these are galaxies that I build in supercomputers.
Yes, and that is something I wanted to talk to you about next. Is tell us about the class that you teach, the simulating galaxies and stars. I find it really fascinating. So yeah, let's talk about that.
Yeah. So most of my research portfolio is on simulating galaxies of different sizes and different brightnesses. And in looking at these galaxies, I'm trying to understand the invisible scaffolding behind them, so the dark matter in these galaxies. And what's nice about building these galaxies in a supercomputer is that I am all powerful. I am able to change certain things and see what happens to my galaxy. So you can think of galaxy simulations as time-lapse movies. And I can rewind and go forward, back and forth, and tweak initial conditions. I can tweak how stars are forming, and I can tweak the nature of dark matter. And so this is what I work on with my students.
So what makes it different to simulate this? And I imagine it is a supercomputer because it sounds like really data-intensive simulation. What is different about that versus just doing the observation or collecting the telescope data? What is the benefit of simulating that?
So when a space telescope, for instance, like Hubble, takes a picture of the cosmos, they're taking one snapshot in time. And from one snapshot in time, we're trying to figure out everything about that particular galaxy, that star, whatever it is we took the snapshot of. What's beautiful about a galaxy simulation is that I simulate it from my pretend Big Bang in my supercomputer all the way to today. And I can generate an image that looks just like it came from the Hubble Space Telescope. And now, since I understand its cosmic evolution, I can say, why does that galaxy look the way that it does today?
Okay, so
yeah. So I can give you the why behind that snapshot.
Behind what the snapshot that, let's say, Hubble Space Telescope is giving you. Fascinating. This sounds like a lot of data. You mentioned supercomputer. Mm-hmm. Is this some capability we have at George Mason, or where do you go and use this, these computers, and where's the data house? Is it at George Mason? Yeah.
It's a combination of George Mason and national supercomputing facilities. So the actual simulations themselves are either run through National Science Foundation or NASA supercomputing facilities. So just like astronomers who actually use telescopes apply for time to use those telescopes, I apply for time to use these large supercomputers. And so I run the simulations on these supercomputers, but the output is also large and the analysis is also data intensive. So I also leverage resources at George Mason through their computing to do post-analysis of the actual simulations.
So in the age of, like I said, I started out saying that in the age of big data analytics, artificial intelligence, which is absolutely, we talk about AI in everything we do now. Is there a role of AI? Is it enhancing the capability of doing the simulations and analysis that you're doing and your colleagues, I would imagine? Is it making is there a shift there, or have you been using artificial intelligence already for a while and new for maybe some of us?
Sure. There are two ways in galaxy formation simulations that machine learning and AI have been used. There are scientists at Carnegie Mellon that are using AI in order to enhance what's called the resolution of the simulations. So this is a very expensive set of calculations to do. We're simulating 13.8 billion years of time in months on a supercomputer, and we're simulating whole galaxies and all the contents inside them, the gas, the stars, the dark matter. And so you can imagine that there's only so small we can make our individual resolution units, and that doesn't necessarily capture, you know, the microphysics of what's going on inside of a galaxy. And so AI can help figure out what's going on within an individual pixel of our simulated galaxy and make some guesses about what's going on in there and enhance the resolution there. So AI can be used to increase resolution, but you can imagine that machine learning can be used to ingest these large data sets and be able to pull out trends about the galaxies. So I have a student who is working on building giant trees of galaxy interactions and figuring out which of these interactions are important for that galaxy's evolution. And in order to do that, she's using machine learning techniques to draw out what are the important characteristics, what are the important interactions. Is it the merging of galaxies? Is it angular momentum that's tugging on them? Is it, you know, close passages of galaxies near each other? Which masses matter? Which ones don't? And those are all questions that, you know, for hundreds of galaxies that we're simulating would take a long time to answer if we couldn't employ machine learning.
So is this a capability that we had? Could you have done this same work 10 years ago, 15 years ago? Give our audience some idea.
Yeah, that's a fantastic question because I get to tell a story. So I wrote my entire PhD thesis on 13 dwarf galaxies. Okay. And my latest, most massive data set of dwarf galaxies is nearly an order of magnitude larger. Right? So we are now in a time where we can make our code scale on these CPUs and GPUs so much better, and these calculations can then be done more rapidly. and with more unprecedented detail and resolution than we were able to do before. So for example, there are people that are running fully what are called cosmological simulations, so from the Big Bang to present day, of galaxies simulating individual stars within those galaxies. And that is incredible. And that's, you know, I don't want to age myself here, but between my PhD thesis and now, that is a huge improvement.
Huge difference in it.
Yes.
Okay, let's talk about, they are, as I said in the beginning of my introduction, how the telescopes are today are really data intensive because we have the supercomputing capabilities to analyze them. Can you give us some examples of some of those data intensive telescopes that you're relying on or that you will make use of?
I want to go a little bit back in time before I talk forward in time. So I'd say that astronomy became really data intensive in the era of what's called the Sloan Digital Sky Survey. And so this was a telescope that surveyed the entire northern hemisphere of sky multiple times in multiple wave bands of light. So from, you know, blue light all the way to red light, because different wavelengths of light can pull out features that you wouldn't necessarily see before. And they really paved the way of making all of that data reduced, so meaning taking out, you know, things that you don't want in your images, and putting it publicly for people to be able to pull and study in the way that they want. And because they surveyed the entire night sky multiple times, it became this repository that people are still using today. And so astronomy is headed from the direction of, you know, the lone astronomer observing on the mountaintop, taking images that only they need and they'll never share unless, you know the person and they hand it to you on a literal disk, or to where we have this large amount of data that is publicly available and available to everybody to do the analysis that they want to do. And so since we've moved in that direction, that's what's happening with all these new missions that are going to happen. So for example, the Rubens LSST is going to survey the entire night sky essentially every 3 days. So this is significantly faster than the Sloan Digital Sky Survey. So you can imagine doing that in multiple wave bands every 3 days, making that available and saying, go astronomers, go. Figure out what's in here and tell us.
Amazing. Well, we are going to come upon a break.
When I was your age, I was just like you, fascinated by stars. But now I get to search for life in the universe. And who knows, maybe life is looking for us too.
So we're like aliens to them?
Yeah. Does anyone want to be a scientist now?
I do.
Awesome. We need more girls in STEM.
Maybe we can find aliens. So how was work?
It was 1,300 hours. My math class from 302 was in the trenches. Davy Roth had it the worst. Fractions were coming at him left and right. He just didn't get the damn things. 2 days ago, I tried to teach him what 1/4 of 1/2 was using different sizes of blocks. Yesterday, I tried again by dividing up pizza. Both missions failed.
Oh no.
But today, I was ready. I created a combat math game where the only way to beat the enemy is to out-fraction them. Davy conquered every last denominator. My game was so successful, the principal is deploying it to math squadrons all over the school.
Anywho, how was your day?
Oh, today my boss treated the office to salad wraps.
Salad wraps.
I know.
150 over 90.
180 over 111.
160 over 110. I had a stroke.
This is what high blood pressure looks like. You might not feel its symptoms, but the results from a stroke are far from invisible or silent. If you've come off your treatment plan, get back on it, or talk with your doctor to create an exercise, diet, and medication plan that works for you. Go to loweryourhbp.org.
If I would have followed a treatment plan, I would not be in this situation.
We're back to the Inside Scoop. Here again, your host.
I am the host, Hina Kazmi, joined by my guest, Ferah Munshi, professor of astronomy at George Mason University. So Ferah, as we were discussing before the break, we were talking about the data-intensive, data-rich, really I should say, the telescopes, and you were talking about LSST and how you're utilizing that data. So I wanted you to just pick up from there.
Yeah, sure. So LSST is already had first light, and they've done some test surveys, and it'll go full blast relatively soon. So this is happening now, and I would love to talk a little bit more about what's happening next.
Yes.
In particular, right, Hubble is turning 35. It is 35 years old, and it has spent 35 years giving us incredible space data. And JWST launched and is looking at slightly longer and different wavelengths than Hubble. But next up, we have the Roman Space Telescope. Roman is one of the few missions that NASA can actually say is running slightly ahead of schedule and under budget, which is huge.
A rarity,
absolutely
perhaps?
Huge. Yeah, it is absolutely huge. And it should launch in the next, well, I will say by 2020, end of 2026. However, we'll see what happens. And one of its main goals is to be the next Hubble, but in a wider, more panoramic view. And so it's going to be absolutely incredible in that its field of view is 100 times larger than Hubble. Yeah.
Wow.
Yes. And so it'll be able to survey millions of galaxies in a single snapshot. And with that, it'll be able to study dark matter. So it can look at the way light bends around galaxies in order to infer hidden mass that you don't actually see, and be able to make large-scale maps of dark matter in the universe, which you can then compare to my computer simulations, right? So I can make as many predictions as I want, and Roman can go ahead and validate them or not validate them. So I can say, maybe I think dark matter is very clumpy, and in these clumps the galaxies form. And Roman will make a map and say, actually, not as clumpy as you think. And then I can say, okay, maybe dark matter isn't so cold, so it isn't so clumpy. I can make it a little bit warmer, a little bit more diffuse. And then we can validate against those maps.
So Roman, and one of the things that I understand about it is that it will scan the sky. So as you said, its field of view is much wider than Hubble's, and it is scanning the sky, night sky, how many times?
So Roman is not scanning the night sky.
I have that wrong.
It's Rubin that's scanning the night sky. That's a ground-based telescope.
Okay.
Roman is going to operate a lot like Hubble, where astronomers put in proposals to look at specific regions of the sky or specific objects.
Okay.
But there are particular surveys that they know that they're already going to do, and one of those in particular that they are studying is basically mapping the structure, the dark matter structure of our universe. So basically figuring out, like an X-ray figures out your bones scaffolding inside your body, figuring out what the bones of the universe actually look like.
And that's what we will get from the Roman Space Telescope. Wow. Now, let's talk about, you have mentioned dark matter, dark energy, if you time dark matter, that's been your focus of your research also. For the audience, a little bit that I know about astronomy, I do know that I'm fascinated to know that how little we really understand about the cosmos, and what a small percentage of the information or the matter that we really understand. But then we have this dark energy and dark matter, which is majority of the I guess, what do you say, that cosmos, it takes place in cosmos, takes up the cosmos. So help us understand why studying and understanding dark matter and dark energy is so important. Give us some,
So to put some numbers on that, right? 85% of all matter in the universe is dark. We can't see it because it doesn't interact electromagnetically, but we know it's there because it's a mass and it interacts gravitationally. So we can infer that it's there, okay? So dark matter is 85% of the matter in the universe, but it's only 27% of the universe. The other 68% is dark energy. So if we were to imagine a pie chart, just a tiny sliver is you and me, right? So we only really can see and understand such a tiny portion of what's actually in the budget, the mass budget of the universe. And what's neat about it is the stuff that's invisible is determining what the fate of the universe, so dark energy, tells us that there is an expansion of the universe, that the universe is growing at an accelerating rate, okay? And it tells us potentially what might happen to the universe at the end. And dark matter basically is the scaffolding that holds together the stuff that we can see. And so it's really important to understand, what is this stuff that we don't know about, that we have no physics to describe, and is there some sort of new physics that we need to discover in order to understand the majority of our universe? So
I want to kind of emphasize on what you just said, because it's so important, and I wonder how many people really understand the significance of it. When you mentioned you and I and a piece of pie, just an analogy, so that is really, and please correct me if I get this wrong, it's all of the matter that we know of, right? The stars, galaxy, asteroids, planets, everything. You're saying all that combined is about a small sliver of information, knowledge that we understand about the cosmos. The rest is this dark energy. Did I get that right?
Yes.
Okay. And then dark energy, and then the dark matter is the 27%. Yeah. Okay, that's fascinating.
Yeah.
So, okay.
Absolutely. I do want to mention, though, right? So I study dark matter in these computer simulations, and I try to validate my guesses based on comparing to observations from telescopes. But there are people out there that are actually building detectors to try to figure out how to detect dark matter in a different way other than just through gravity. And in building these ultra-sensitive detectors, and for some of them, they have to be cryogenic if you think of dark matter interacting in a certain way. In the process of doing this, we've figured out different ways for imaging. So MRI technology, CT scan technology has come from some of the direct detection experiments. A lot of AI image recognition and detection has come from dark matter experiments, as well as some of these big data analyses looking for small signals in a large amount of data have been used outside of astronomy in finance, for example. And so, yes, we're applying it to finding dark matter, but the techniques and the technology that get developed to look for this elusive thing has applications way beyond astronomy.
Yeah. That brings me then to my next question. So relating help us relate the scientific research that you do and how, as we are in the midst of this new commercial space boom, and the thing that we normally right away connect with is the human space exploration. So we know the Artemis 2 mission will launch hopefully soon, and it'll be the first time we will go around the moon and with the purpose of setting base on the moon. So there's a lot of excitement about that, and of course eventually going to Mars. So help us understand, how does what you study and your colleagues, how does dark energy, understanding dark matter relates to, or if it does at all, to the other side of which I would say cool, fun stuff that normally I know my kids relate to, which is the human space exploration and going back to the moon. So help us understand that.
Yeah. So we're at the beginning of humans kind of venturing out beyond our atmosphere into space, right? So, we have all these plans to build a moon base. There's the moon, there's moving on to Mars, right? So you can see that our horizons are expanding, right? And in the far future, right, we're going to want to expand beyond our solar system. We're going to want to maybe move around in our galaxy, right? You can think of the Star Trek universe. You can think of, even the Star Wars, whichever side you prefer, universe, right? And dark matter is the majority of that universe. It is the backbone for what we can see. And so you can imagine early explorers kind of leaving with their ships, right, trying to explore new lands on Earth. They maybe didn't understand what the currents were doing, right? Dark matter sets the gravitational currents as we start to explore. So you can imagine, yes, we are just venturing out into our little bays, beyond our little bays, moving out into the grand ocean. But you can't just understand your bay and think that the ocean's going to act like that. So you have to understand the dark matter. It's like the currents in the ocean.
That's a really good analogy. I like that. So, of course, moon is the first step. You know, in the future, our hope is that we go explore and land rovers, robotics missions, but also humans going to asteroids, mining the asteroid. Exactly. That is a big hope. So, understanding I really like the way you're explaining it. The ocean, really, in between all the hard objects that we see, and that's what dark matter. Understanding dark matter is. Yep. That's wonderful way to say it. Okay, so let's continue on. Let's talk about, you know, there have been many firsts just in this 21st century, and I'm just fascinated by that. For example, you know, and I really say that we've had many firsts since, not only just since the dawn of time, but really the first known telescope that was built in 1609 by Galileo. So given the centuries of astronomy and scientists observing the skies, here are some few very important firsts we've had just in the past 20 years. So for example, we, for the first time, touched the sun. So we had NASA's Parker solar probe, which entered really the corona of the sun. So it's like that's the first time we ever did that. First floating planet was observed, which means that it is not tied to a sun system, like a solar system like our own. It's a floating planet. First exoplanet with an atmosphere observed, much like our atmosphere, and evidence of black hole. And something I think you already mentioned, just we have for the first time, full map of the Milky Way, our own galaxy. So many firsts have happened, and what I'd like you to then talk about, what are you looking forward to? What are the next 10, 20 years where the research is now that you are seeing, that you're projecting that we will have some significant findings? So yes, we should talk about that.
So I am really looking forward to the Roman Space Telescope, as I've said, but also beyond that, the LISA Space Telescope.
So it is time to take a short break. Please stay tuned as we continue our conversation with Dr. Munshi when we return with more Inside Scoop.
Nice going, Spencer. I can't believe we broke Old Man Hennessy's window.
Correction, dude. You broke. I just threw the ball.
This is really bad. What are we gonna do?
We? Go to the door, ask for the ball back.
Are you serious?
It's my ball, Myrtleback.
You're so dead. I'd run away.
Yeah, to Uruguay.
Kiss your life goodbye. Sorry.
Let's go. See you, dude. See ya. Remember me and your well.
Nice one. Some friends you are. Hi. Tell him it was an accident. And we can fix the window. Come on. I'll come with you.
Loyalty. Pass it on.
You go first.
A message from the Foundation for a Better Life.
One day these rats were playing in the woods. Well, it's some matches and that's no good. Listen to smoke before you give it a try. Only you. Don't play with matches. Don't play with fire. Cause there's nothing very funny about rigged out fight. Nothing very nice on a homeless mind. So if a gorgeous force is what you desire, don't play with matches. Don't play with fire. Yeah.
Only you can prevent wildfires.
Fire.
We're back to the Inside Scoop. Here again, your host.
Hi, I'm Hina Kazmi, joined by tonight's guest, Dr. Ferah Munshi, professor at George Mason's College of Science. So Ferah, before the break, we were just starting to talk about all the breakthroughs and the very first we've had just in this past 20 years. So tell us about what are the, given all the advancements in telescopes and the big data age that we're in astronomy and astrophysics, what are the discoveries that you're waiting for and that you're anticipating in the next 10 years, 20 years?
So I'm going to start with now in the sense that I'm going to chat a little bit about what James Webb JWST is telling us right now. So James Webb has been peering back in time further than we've ever seen before. And in doing so, we're getting as close to the Big Bang as we can get. And it turns out that galaxies are evolving faster than they should be. They're more massive, way too fast. The black holes that live in their centers are more massive than we expect them to grow. And there are all these questions that are emerging from this data. And these questions, yes, we can keep taking JWST data and analyzing it, but some of those answers might actually come from these next-gen space telescopes. So I've mentioned the Roman Space Telescope, and Roman will actually be able to study these galaxies and provide different wavelength data about those galaxies that we can combine with JWST to have a more detailed picture about what's actually going on. We'll actually be able to map out larger portions of the early universe to try to understand statistically what's actually going on. So do we just not have enough statistics, and that's why we think things are going wrong? Well, Roman will be able to do that. So we'll have large-scale maps of galaxies, large-scale maps of dark matter to be able to answer some of these questions that James Webb has brought to the forefront of thought. The other thing that I want to point out is these are all telescopes that we use our eyes to look at. We have gravitational waves now. We've been able to detect gravitational waves. So LIGO on Earth has been able to detect gravitational waves from stellar mass black holes merging together, okay? But we have LISA to look forward to. And what LISA is essentially a gravitational wave detector in space. So you're going to have 3 satellites, thousands of miles apart, firing precise lasers that are going to be able to detect motion in space-time that correspond to gravitational waves to be precise. And the way that they're aligned and the baseline that they have between these satellites makes them so that they can detect gravitational waves from the early universe, even further back in time than we've actually been able to see with our eyes. So we'll be listening to the early universe using LISA. Yep. And so I like to say that we'll have astronomy reshaped because Roman will give us the backbone of the universe, but LISA will allow us to listen to the heartbeat. And we'll be able to understand the supermassive black hole mergers that are happening so far back that we can't peer at them with telescopes. So we'll be able to explore the cosmic dark ages. And so the combination of the two will give us basically insight into the universe that we haven't been able to before. And even get so far back as to understand the Big Bang and how the universe kind of accelerated from that Big Bang. So insight into dark energy as well.
So are you saying we could actually hear from the gravitational waves, we could actually hear the Big Bang? Is that what it means?
There are people who think that the Big Bang should have emitted primordial gravitational waves, and LISA should be able to detect them.
Okay, so for our audience, would you explain wavelengths? So that's light, wavelengths across the spectrum, a lighter spectrum versus the gravitational wave, which is really the sound waves, or not really sound, I said it wrong, but could you just help us differentiate? What is, when we talk about different wavelengths of astronomy, what does that mean?
Yes, so we see with our eyes, and our eyes specifically see what are called visible wavelengths, right? They're sensitive detectors to basically the rainbow. That is only one small sliver of what's called the electromagnetic spectrum. So we have from gamma rays all the way to radio waves. And those waves essentially have a frequency or a wavelength associated with them. So gamma rays are really short, radio waves are really long, right? And the visible spectrum is somewhere in between. And telescope detectors can be made sensitive not just to what we can see with our eyes, but to these high frequency and low frequency waves on either side. And that allows us to see things that maybe weren't visible in the visible spectrum. So for example, our Milky Way has these dust clouds along kind of the plane of the Milky Way. And in the optical, those dust clouds are a problem. You can't see through them. However, if you shift to the infrared, they are no longer opaque, and you can actually see what's going on where the dust clouds were formerly blocking your view. So multi-wavelength astronomy is really important because in different wavelengths, you can study different objects or maybe see things that you weren't able to see before.
So the telescopes really help us see in those different wavelengths, from gamma rays to X-rays to, like you said, the visible light.
Absolutely.
And it gives you that multidimensional, I guess,
exactly,
characteristics of galaxies or whatever object you're observing.
Exactly.
And so gravitational waves are fundamentally completely different. They're not part of the spectrum.
You can think of them as ripples in space-time.
Okay.
So they are not electromagnetic.
They're not electromagnetic waves,
exactly.
yeah.
So you can't see them, and the way we detect them is through these lasers, but the best way to visualize them is actually through sound.
Through sound. Yeah. Amazing, fascinating stuff. So, so we were coming back to, what do we look forward to? What do we anticipate? We will learn about the cosmos, and maybe even the the age of the universe, right? So, with these findings, possibly that James Webb is making, is challenging some of those understanding. The way you explained it, what would that mean for everyday person? How does that relate to us? Help us understand. Why does it matter if the age of universe is 1 billion longer or 2 billion years longer, light years than we initially thought? How does that change our understanding then?
It changes kind of how we understand physics, right? So if we had always assumed that the universe was a certain age and structure formed in a certain way, and galaxies formed within that structure in a certain way, stars formed within those galaxies in a certain way, all following these physical laws that we thought that we understood, that goes all the way down to, how did we come to be, right? And if all of that physics is wrong, then do we really understand how we got here and how we came to be? How can you understand how planets form if you have no idea how the universe actually formed and how that structure propagated out to give a place for a planet to form? And so I think it's just so fundamental to the question of how did we get here is how did the universe get to be here?
Very, very fascinating. So let's talk about now where we are today, not just in space exploration, coming back to George Mason, where you are a professor. Now, I mentioned in my introduction that one of the core research areas that George Mason University and leadership is focusing on is on space exploration, collaboration. So help us understand why that should be a core research area. Is it for all the reasons that you just talked about? Because seems to me that we're at such a cusp of learning such fundamental things about the universe, the cosmos, then eventually, of course, how our planet came to be. So are these the reasons? Help us understand how Grand Challenge Initiative and how the space exploration is one of the core 6 areas of research.
Yeah. I think the core case for space research is that it's not just a choice between understanding science and spending your money on social needs or spending your time understanding social needs. Space research is supporting social needs, right? So when we are studying space, we're inventing technology that can help people here on Earth. Space research includes studying near-Earth objects and whether, an asteroid's heading in our direction and keeping track of that, right? Space research includes understanding how the physics of the sun affects us here on Earth. So coronal mass ejections, big flares on the sun, will they knock out our cell phone towers? Will they knock out our power grid? That's all part of space research. That's called space weather. And all of that falls under the umbrella of space research when we're talking about the grand challenges at George Mason. And so also under that umbrella is, aerospace, right? So doing space research improves our aerospace industry. And right now that is, by 2035, it's expected to be $1 trillion industry. So training that workforce is also key under this space GCI pillar. Not doing the science is also detrimental to us, right? So you can imagine that, just because, we may not necessarily have the funding right now to study things that we want to study, that doesn't stop other countries from being able to do it. So if we want to keep this economic lead and the lead that the US has on science, it's really important for us to address, moving science forward.
I really like the way you're relating how the, when we think of astronomy, astrophysics research, just scientific research, how to relate it to really things that are directly relevant to everyone. Mm-hmm. For example, tracking the asteroids and space weather, which I know is very relevant to us because we rely on so many digital devices, mm-hmm. and satellite communication, which is directly impacted with due to space weather. So really relevant in that sense. Mm-hmm. I think what we will do is should talk about the Grand Challenge Initiative now. In that sense, there's a lot of science and a lot of research going on at George Mason already, even before the Grand Challenge mm-hmm. Initiative was set up. So I would like you to kind of help our audience understand all the wonderful work goes on at George Mason related to space research. I will tell you that a lot of my friends don't realize that there's even an observatory, a real observatory at George Mason Fairfax campus. So let's talk about on all the various space research centers that we have at George Mason.
I will do my best because there is so much. I can start with space weather because I brought that up. The space weather group at Mason is actually top of the line and one of the best in the country. They study everything from solar activity to weather in between the planets and atmospheres of other planets as well.
Okay, I want you to hold that thought because once again, we must take a short break and then when we will conclude our final segment and talk more about the science happening at George Mason and the science funding when we return with more Inside Scoop.
Okay, so we drowned the fire, yep. Stirred it, mm-hmm. drowned it again, mm-hmm. and now just feel if it's cold.
Yeah.
Cool.
Smokey just gave me a bear hug.
I know. Already posted it.
I got a crick in my neck, limp in my step, cramping in my muscles every time I try to flex. But if you throw me love, I'll throw you some more.
It's a big responsibility.
Oh, it's huge. I know, it's huge.
And the salary.
Oh my god, yes.
Right?
I mean, like, I was about to move in with my parents, and right before, so this saved me.
I really believe in you, you know.
Thank you. It's nice to hear that from someone.
These are cool. Did you, what did you?
we're back to the Inside Scoop. Here again, your host.
Welcome back to Inside Scoop. We are speaking with Dr. Ferah Munshi. And as we were discussing before the break, you were kind of helping us understand various types of space research that we're doing and the research programs that we have at George Mason. So I'll let you.
Yeah. So I was mentioning that we have a large space weather team that works with the government in order to understand how space weather will affect humans here on Earth. George Mason, just in the last couple of years, got its first funded space mission. So Dr. Peter Plavchan of the same department I'm in the College of Science, is working on building the satellite that he's going to launch into space. And this is all funded by NASA and supported by George Mason. It's fantastic. I also want to mention that there are a lot of researchers that are thinking of what happens to humans when we send them into space. So my colleague, Dr. Anna Maria Beria, is working on simulations of these human factors. So making little artificial astronauts that are, say, on the moon base that we're predicting for Artemis 3 and 4, and what kind of characteristics are most successful in that astronaut and that team of astronauts to be able to effectively do the jobs that they need to do on the moon bases. So there's some fantastic stuff going on. And that's looking upwards. There are a bunch of scientists also looking downwards. So you can imagine that these satellites are monitoring the Earth. They're looking at climate change. They're looking at migration patterns. They're looking at all sorts of things that are going to affect the longevity of humans on Earth.
So that's the Center for Earth Observation Research. Okay, and also I do know I want to mention that that with the PI-led the Landau mission, what I understand is that we'll have an actual mission control room right here at the Fairfax campus.
Exactly.
Which when is the? So I want our audience to understand that we will actually have the launch operation, on-orbit operation, being conducted out of the George Mason campus.
Yep.
That's really exciting stuff.
Yeah. And we're hoping to do more of that, right? So with the Grand Challenge Initiative really backing space research, we hope to be the place that launches these relatively small missions in partnership with aerospace, in partnership with multiple departments across the university that are all dipped into this kind of exploration of space to be able to become kind of the key small satellite place to be. Yeah. And in doing so, right, we're giving students the experiences of being able to design instruments, being in mission control. What does mission control look like? What does it actually mean to launch something? And so it's going to be an absolute transformation of what a university can do when it comes to space.
And right in our DC metro area, in Virginia especially, we have basically all of the new, I would say, new and traditional space, their branches within, whether it's the Western Corridor or what. So there's a lot of opportunity for the university and for the students and the research to partner with them. I know that is something we've been looking into as part of the Grand Challenge Initiative too.
Absolutely.
So so
I would also be remiss to not mention the growth that's happening in partnership with George Mason in Manassas, the new innovation district that is popping up there. And so the Innovation District is not just academic, it is partnering with local community colleges as well as industry, bringing industry in to live in to be located in the Innovation District and partner with the university in developing new technologies. My interest is in aerospace and in space, so that is definitely happening, but it also is happening for bio and other aspects of research going on at George Mason.
I'm really glad you mentioned the Manassas campus, because sometimes I know I don't venture out there, so it's good to hear about that. Really exciting stuff, and I'm really proud that we can do all this work right here in George Mason campus. All right, so let's talk about, when we talk, space policy. We started out with science as a special topic for when we talk about space policy, and for me, the space policy really relates to science funding. So earlier for the fiscal year 2026 budget, there were some concerns, and NASA will see some significant cuts, especially in the astrophysics and the just various science mission directorate at NASA and NSF. We are beyond that. FY26 budget has retained all the scientific science funding, which is great news, I know, for you and your colleagues. Now, I think what I would like you to maybe spend a few minutes and talk about the rationale for sustaining the science funding. Now, yes, we are in the new commercial space boom, and there's a lot of excitement, and we want to keep the momentum going. The U.S. is in the lead in this commercial space era, so we want to maintain that leadership. That said, there are a lot of social challenges, social programs that need to be funded. There are a lot of shortfalls in different buckets of funding that the government has to think about. From your perspective, what would be your rationale to say we have to keep sustaining and maintaining, if not leading, the scientific funding as a priority in the big realm of space policy, national space policy? Now, I ask that knowing that you're a scientist. Of course, there's some bias automatically. That is okay. But I think it would be good for our audience to understand from a scientific perspective, what is the rationale that we maintain this funding and not, at risk of making significant cuts?
So I think it's important to remember that NASA is not just funding these big flagship missions, right? NASA funds a whole lot more than that. And in particular, it's a public safety and service that NASA offers, in the sense that weather forecasting, it falls under the umbrella of NASA. Disaster response, communications, satellites, all of that are things and technologies that are developed or monitored based on NASA science. And so, I mentioned space weather, I mentioned near-Earth objects, I mentioned looking down back and monitoring Earth. Those are all things that keep our technology going, that keep us moving forward in our daily lives, and cutting a NASA budget could remove some of those things that we've come to rely on. I want to say this in a good way. It really destroys momentum forward to have to wonder what the budget's going to do the next time it needs to be approved. And so if you want to keep the momentum that we have as being a leader in aerospace, in space, in exploration, it can't be a start-stop. And so things like the GCI can plug those holes, right? So you can imagine that getting state funding through the university to keep us going and keep us moving forward is great. But if the government is stopping and starting that funding and there's all sorts of uncertainty, that momentum really gets truncated.
Yeah. And especially because developing the certain space missions and doing this research, the type of simulations you do, these are time-intensive projects also. Exactly. So having that reliance on the, okay, we know in the every 9 to 12 months that we go through this challenge of a federal budget, what you're saying is that, hey, we cannot, scientists don't live on that schedule.
Exactly.
They're looking long-term, and they have to count on those funding available and the programs funded. Is that okay?
Absolutely, yeah.
Okay, let's see. So to your point that how the scientific research really needs to depend on the sustainability of those funding, and not always looking out for the grant funding will be cut or not, or will it be there for the next fiscal year. What can the citizens do to help advocate for that? What would you want the audience to? What would you want our audience to help us with? Yeah.
So I'm going to throw it back to how you and I met, right? So you and I met by being thrown together to go lobby our senators to continue space funding, and in particular, that day we were lobbying for the Roman Space Telescope.
Roman Space, yes.
And so I'm going to riff off of that a little bit, in the sense that pick up the phone, call your senator, say, hey, NASA's important. We need to keep the budget where it is, at the very least, to be able to sustain that momentum forward, to keep doing what we're doing, and to keep keep that momentum that I'm talking about going. Write letters, do what you need to do, and also keep excited about it, right? Read about it and engage with it, right? A lot of scientists do a lot to have public engagement. So for instance, at Mason, you mentioned that there's an observatory on campus. And I do want to mention that they have public nights at the Mason Observatory where you can actually go and look at Jupiter. You can look at whatever's visible, right? Because it is a relatively small telescope and we do have light pollution, but there's a lot that you can see with the telescope there. I want to mention that they have space camps for kids that run all summer where they actually get to take astronomical data and look at it and play with the telescopes as well, so 4th grade and above. There are robotics camps that are happening, right? We engage so much to make sure that you understand, a citizen understands, what comes out of the space research that is going on. We have a space day every year where astronauts are sometimes keynote speakers. We have activities set up for students and from elementary age and above. We have our mobile planetarium set up.
Yeah, and I do want to say about the Space Day. I attended it past couple of years and I was blown away with all the impressive research that's going on. So I learned a lot, even though I've been affiliated with the George Mason for so long. I learned a lot of all the exciting research that's going on. So Space Day is a very exciting, it happens in fall. Fall
usually typically in September.
In September, and definitely a good way to learn all the research that's going on, scientific research going on campus. Well, you make a really good case to not only maintain the funding, but how I think what's important, what I want to conclude with is how all the scientific research is not just for the sake of research. It really directly is relevant to so much of the things that we rely on as we are in this space age. Basically, we rely on satellites as critical infrastructure for all sorts of communication, for earth sciences, and to monitor weathers and weather disaster, and to plan for them, and GPS. So it is really important that the work that's going on and the work that you and your colleagues do. And I really want to thank you for being here with us. It's been a really insightful discussion and
I've had a lot of fun. Thank you.
Thank you. We are coming to the end of our session at Inside Scoop. I want to thank my guest, Dr. Ferah Munshi, for such a delightful discussion. Be on the lookout for our next Inside Scoop special topic, which will be in space policy, intersection of energy and space. In the meantime, please make sure to tune in to Inside Scoop Live Monday evenings at 8 p.m. Thank you.